Okay, just 1 minute. Yeah, Nikhil, you can share the screen. Please show the code also of PCA. Yeah, Nikhil, you can share the screen. Oh, okay, okay. And show me the code. Okay, just 1 minute. Uh, okay. Data drop NA, clean, data clean. Data clean dot select D type and P dot include. Data dot data dot clean, select D type, include NP number. What is NP number here? NumPy function to find numerical value. Numerical value to find numerical value from where? Find numerical values from select only numerical columns excluding sex or the categorical. Oh, okay, okay. But how we can write NP dot number? How NP know that? Go up little bit. NP include NP dot number. Can you okay? Can you just print NP dot number individually? Class NP numpy number. Numpy number. Okay. Data clean dot select data types include NP number. Oh, okay, okay. I understood. Okay, okay. Go up. Okay, it is including only the data types. Data type which is number. Okay, okay. Data clean dot select data type. Okay, data types. Okay. So NP dot number is numpy number. Number that is the data type. Okay. So it is saying that select only which is a number data type. Okay. Okay. Then scalar standardizing. All right. Then K means n cluster 3. Okay. 3 clusters. But wait. I think we just have two. Can you try with the 2 clusters? I don't think we need 3. here. K means, wait. Perform K means, you're performing K means and PCA both. K means cluster after PCA. Perform K means cluster before PCA. Okay, you are doing PCA. PCA is for reducing the dimension. Okay, that is fine. But why we doing the K means? K means for clustering. K means is for clustering. Okay. All right. So you're doing clustering before it. 3 cluster it will make. Okay. And clustering before, yeah, 3 due to there. One more where it mentioned not available. Acha, acha, okay. Not available is also there. Okay. 3 clusters. Okay, it will make 3 clusters. Fine. Then PCA again with the 2 components. Okay, and then with the transform. Okay, then you're doing PC again for 3. After like reducing the dimensions, we are doing PC again. Okay, and we are subplotting. Okay. Okay. Mm-hmm. Subplot doing okay. So data scaled. The yellow dot is centroid. I know. Mm. Okay. In K means it's always centroid. I know. Go up. Okay. Your first plot is for like data scaled. Okay, data scale cluster before PCA and principal components. Right now, after that, it's principal component. Okay. Data scaled. How many feature does it having? Okay, so you are taking only Kalman length, Kalman depth, only these two. Okay, Kalman length, Kalman depth. Okay. All right. Okay. All right, Kalman length and Kalman. Okay, now show me the graph. Hmm. Before PCA. It's before reducing the dimension, it is looking like this, and after reducing, it became very clear now. Yeah. Remove the centroid from the after PCA. There is no use of yeah. Let's start. Like there is, I think, cluster component cluster. Wait, wait. Where is it? How is it? How is it making that cluster centroid? How is it making that centroid? Okay, go down. So the main summary is that after this, the main summary is that after doing PCA, it becomes very clear that which one is yeah, you can easily classify this is a use. Okay, let me tell you the advantages and disadvantages of PCA today. Let me share a screen. Key points in the code. So, okay. So key point in the code is standardizing the data. Okay, leave this. Interpreting PCA. PCA component. The new feature principal component are the linear combination of the original feature. The first principal component captures the most variance, usually. The second captures the second most, and so on. Explained variance ratio. PCA provides the ratio of variance captured by each principal component, helping to decide how many components to keep. Application of PCA, like why we should use this. So basically, it reduces high dimensional data to 2 or 3 dimensions for visualizing. You can see that in Penguin data, we have how much of features were there? 4, right? So if you use 4 dimensions, you will never make it. You will never able to make the graph. But if you are using PCA, you can decrease the dimension. Okay, noise filtering, like reducing noise by keeping only the most important feature. Feature extraction, creating new feature, principal component that captures the essence of the data. Yes, extra features, or you can say extra things, you can cut it down using the PCA. Pre-processing for machine learning, like simplifying data to improve the performance of the algorithm. You can say the PCA makes the data very pure. You can say that. It reduces unnecessary variance in the data, right? As you can see the graph which we are talking about, this one, this one. Just 1 minute. I think just 1 minute. Yeah, this one. See, all the unnecessary, you can say the height it was taking a too much. Now it is reduced to this much only. So it is easier for machine learning to train the model. So simplicity, advantage of using PCA. Simplicity, PCA is straightforward to understand and implement. Dimensionality reduction helps reduce the complexity of the data, making it easier to work with. Improves efficiency, reduces computation time for machine learning algorithm for lowering the number of features. Yes, very nice. Your machine, if you train on the machine learning, it will take very less time. So you can say it's just like standardizing. You can do standardizing of data as well as you can do the PCA both. Standardizing will reduce the extra variance in the terms of you can say in the terms of data in the rows, and PCA can reduce the variance within the graph. Both the things. But what is the disadvantage? We have some disadvantage of PCA also. Loss of interpretability. The new principal components are combination of the original feature which can make them harder to interpret. So the new principal components are combination of original features. Features. Lot of features makes one PCA. So it is sometimes become hard to get back, which makes them harder to interpret. Like within one PCA, you cannot go back to the lot of feature which it made it. This is what it is saying. After compressing image, for example, after compressing image, you cannot go back to the high definition image. That's why. Assumes linearity. PCA assumes that the direction with the most variance are the most important. Assume that the direction with the most variance is the most important. Yeah, as we made yesterday also, suppose your data is showing lot of variance in this direction, you know, you can see like this. PC assumes that a direction with the most variance. So you can see the most variance is among this are the most important, which might not always be the true. Yeah, like basically sometimes your data could be spread in a circular way also. So you cannot decide like which PCA you want to take, this one, this one, this one, or this one. So there is a confusion in the PCA also. But if your data is very clear that it is having, yeah, if data is very clear that it is going linear, then it is okay. You can easily make the line like this. But if it is very rounded, like this, it becomes very hard that which one should we take, this one, this one, this one, or what. Sensitive to scaling. PCA is sensitive to the relative scaling of the original feature. So it is also sensitive. PCA is sensitive to the relative scaling of the original features. What is summary? So PCA is a powerful technique for reducing the dimensionality of large data set while retaining most of the important information. Okay, see, one thing is there that you can, if it is reducing the dimensionality of lot of features, but still, still you should not take a data which is having very high columns feature, right? Because then it will start, not, it will not compress it, it will start confusing. Then you will not see very clear diagram like this one, this. You will not see very clear diagram like this. So you will be having a lot of clusters. If there is lot of features, lot of clusters will be there. Okay, let's just 1 minute. Let's come to the this topic, t-SNE. Okay, so what is t-SNE? What is the meaning of this? So the meaning is tree distributed stochastic neighbor embedding. This is also sometimes similar like the PCA, but sometimes it performs better than the PCA. It is also for dimension reduction and classification. We'll see to these graphs later. But first of all, let's do a little bit of theory about t-SNE. The t-SNE is popular dimensionality reduction technique, particularly used for visualizing high dimension data. See, it is same like PCA. In a low dimension space, typically 3D, 2D, it's especially effective for non-linear data, where PCA might not capture complex relationships. So basically, this is also for you can say non-linear data. For example, like this, your data is there, and your data is making very non-linear kind of structure. You can see now your data is not going in a straight line, it is going like this. So in this type of scenario, we should use t-SNE in non-linear data. How t-SNE works, by the way. So preserving local structure, like t-SNE focus on preserving the local structure of the data. It tries to ensure that similar data points in high dimension remain close to each other in the lower dimension projection. For example, this one. Yeah. So you can see there is two clusters. So now the t-SNE will try to project them in a line, and still it will try to make that yellow will be on the one side and your blue one is on the other side and the red one on the other side, so that you can easily, you know, classify them easily. Probabilistic approach, instead of using direct distance, t-SNE calculate probability of similarity between points in both high and low dimension. It minimizes the difference between these two probability distribution, preserving cluster of pattern. So after, you can say, after following a product projecting in a line, then it clustered itself according to probabilities, according to the like features. If they are similar, then they will be clustered. Clusters and separation. t-SNE excels at highlighting clusters in the data, making it ideal for understanding the grouping of data points that might not be immediately obvious in higher dimension. So yes, so t-SNE excels at highlighting clusters in the data. So basically, it makes cluster just like the k-means, right? Okay, so what is the difference between the t-SNE and PCA? Basically, PCA is a linear technique that maximizes variance, best for linear data, but t-SNE is the non-linear technique that preserves neighborhood information, best for non-linear, right? As we I have shown you here. So basically, sometimes it works according to the distance. Okay. So because each point, okay, let's talk about the like this one. You can easily see there is three clusters here, right? So if we talk about this black one, what is the distance among this black one and all the yellows? You will see that these things, if you calculate the distance, if we if if you're talking about a line, so it will be high, having a high distance, right, from these yellow points. If we talk about this black and blue, you will see that black and blue is having a very less distance. So it is very nearby. And the same goes with the red one. Red ones is here, which is very at very distant. So if you make a curve, this curve shows that high peak shows that there is a very less distance among them, right? So ultimately, we measure the distance between the all the points and the point of interest. So we'll try to measure like taking the one point at one time and calculating distance to all of the other data point. So plot them on the normal curve. So and then measure the distance from the point to the curve to get the unscaled similarity score with respect to the point of interest. So this is how normal curve you will get of distance. This is called mapping of distance on normal curve. So this is normal distribution, and it is a distribution of distances. Okay. So you can easily understand that. See, near points are clustered together, far points are clustered together. So you can see easily classification is happening here, right? Uh, it does not matter your data was linear or non-linear. See, it is also making non-linear structure, right? If you use PCA, if you use PCA something like this, then all the point will be projecting on that, and sometimes it might produce some kind of confusion, because suppose your suppose principal component is making this way. If you project on that particular line, right? If you project these points, then you will find that this here, the blue and red are making confusion, right? In the PCA, but it will not be the case in t-SNE. t-SNE is also projecting them on a single line, but it is easily classified because they are working according to the distance. So that's why it said like whatever distance we have in the high dimension, this is high dimension and this is becoming low dimension, it is preserved. That's why we said here. Where is that line? This one. t-SNE focus on preserving the local structure of the data. It tries to ensure that similar data points in high dimension remains close, see, to each other in the lower dimension. So structure is remain preserved even after projection. Let's see some kind of, I think, animation. t-SNE GIF, if I'll get it, I'll show you how these things are done. See this graph. There was 3 clusters. We projected on the single line and it seems very messy. See, but we are taking the perspective of each point and calculating distance. Suppose this is the point and we're calculating distance from each point. Now see, they are making clusters now. See, automatically they are clustering themselves. See, this one, see, this is final. Are you able to understand what I'm saying? Yes or no? Okay, okay, tell me how it is clustering itself here. How this movement is going on. Why this movement is going on. What approach is taken. Yes, right. Distance, right. Okay. Okay, let's try to understand like how we can code this. So SQL data sets, load iris. We will perform on the iris data only. Import the t-SNE, import the matplotlib, load your data, all the data in X, target in the Y. So applying t-SNE with the two components. So t-SNE, we are taking the component 2, random state 42, and then fit your data in t-SNE. And after fitting, how does it look like? Let's print that before we print any graph. Yeah, 2 points are given here. For a single point, two coordinates are given. Okay, so we are making scatter plot of first feature as a x, second feature as a y axis, and color we are doing according to y. Y means the target data, which is three colors 0, 1, and 2. We reduce as color k, black, size of the point 100. So this is the first component. This is second component in a t-SNE. See this how it is clustering. See, the distance is preserved. Distance among this cluster and this cluster is very much. But why these both are sticking together? Can anybody tell me? Why these two flowers points are sticking together? Yeah, very mild difference. Correct. Because if you check their petal length, petal width, sepal and sepal width, there is not much difference. That's why it is falling in. There is not much distance between them. That's why. That's why. Yes. Okay. So I think I should give you one data. Okay. You should also try the t-SNE just one minute. 1 minute. Okay, so some data are coming here, which we can use. Okay, here we have a lot of data. Sample submission, dimensional reduction, PCA, and wait, let us use. Okay, some data it is saying MNIST. Let's try that. IST. Yeah, this data is very nice, but I think it's very large data. To 10 classes to CFAR 10. Okay, we have stock market data also. Seven columns. Yeah, this is fine. So a this is data of what? Stock market data for the S&P, sale and purchase. So it says stock market data can be interesting to analyze and further incentive. Strong predictive models can have a large financial payoff. So date is there, price of the stock at open, highest price in the day, lowest price, number of shares, and name, stock ticker name, high, low, close, volume, name. All right, I think you can just make the classif- classification using the t-SNE. You can use it. This data is also very big, by the way. I'm giving you this data because I'm getting a lot of data, but we have already used it. Let's not use the data again, like wine data, breast cancer, iris. You can try your t-SNE on this data. All the description you have written it over here. So you have to make clusters.
हाँ सॉरी सर, ये कॉल चल रहा था, घर में थोड़ा सा इशू है।
Very nice. You joined just 2-3 minutes ago. The amount of financial data web is seemingly endless. A large and a well-structured data set on the way array of the companies can be hard to come by. Here I provide data set with historic data of last 5 years for all the companies currently found on the S&P. Okay, so it's a 5 year data by the way. The script I use acquire is CSV file. GitHub repository is also there for it. Try to make the clusters of this. All right, yeah, and you can see the recording for the code is also there. All right, so all right, rest of the things we will do in the next session. If you need some help you can tell me. This is the code. Just transform in two components and try to visualize it. If you feel like that you also need to standardize, you can do it. All right, students. So have a good day. We'll meet you next week. Welcome.